So today what we're going to be working on is an introduction into series. Now a series is basically a list of numbers, and what we're going to be doing today is we're going to be finding predictable patterns within the formula so we can jump ahead in that sequence. That way we don't need to list out, like let's say the 100 terms. I don't need to count out the first 100 numbers to find the 100th term. Now at this level, a series is going to come in two different forms. We're going to have an arithmetic series, which is a sequence of numbers that changes via either adding or subtracting or a difference. Kind of like what we see here, 1 plus 2 is 3, plus 2 is 5. We're adding the same thing each time. Conversely, we have a geometric series, which does the same either via multiplying or dividing. A common ratio is what we call. So that would be like 1 times 2 would be 2, times 2 would be 4, if we're multiplying by something that is the same multiplicative factor. It's what we call the common ratio. Now, we can come up with a couple different ways to do this, but the general idea is that to find a spot in a series arithmetically means we're going to find what we call ace of n is going to require ace of 1 plus the difference times n minus 1. And we've got a couple things to label here. We know our ace of n is our desired term. So if we want to find, let's say, the 10th or the 100th, it's got to be our ace of n. Our ace of 1 is going to be our first term. Now, our d is our difference, or our common difference. And our n, which is our last thing, is going to be the number of terms we have to go. So if this is the first term, that's why it's ace of 1 in place of the n. Let's say if we're wanting to go 5, our n would be 5, the term position. Awesome. And now let's kind of break down what this formula is saying. It's saying if I want to find, let's say, the 10th spot in line, I take my first number, and I add whatever the difference is. So in this case, I'm adding 2. So I take 1, and I add 2, 10 minus 1. I add 2 9 times. That makes sense, because on the first number, I don't actually add 2. So for my first spot, 1 minus 1 is 0. I don't add a difference to my first number. That makes a good bit of sense. The same setup is constructed using our geometric series. To find our position in line, so our desired term, we're going to take that first term, ace of 1, but instead of adding a difference, n minus 1 times, we're going to multiply it times the ratio, n minus 1 times. So again, if I want to find, like, let's say the third spot in line, I'm going to take my first number, multiply it times the ratio, 3 minus 2, 2 additional times. So let's say 1 times 2 is 4, times 2, 1 times 2 is not 4. 1 times 2 is 2. 2 times 2 is 4. So the same setup is in both of these, except for in this case, we have our r is going to be our ratio. Awesome. So we still have our first term, our desired term, and all that good stuff. So let's try and see if we can put this to use. So for our first number here, I have a pattern of 1, 3, 5. Now, first what I want to do is I want to check, saying, okay, let's take 3 minus 1, 5 minus 3. I want to take some position in line and subtract the position before it. So 3 minus 1 is 2. 5 minus 3 is 2. Perfect. So I know I have a difference of 2. And that's really what we wanted to see. I'm adding 2 each time, and the way I do that is I take, let's say, spot 2 and subtract spot 1. So I have a difference of 2. So using my formula, I know that whatever position I want to find, I'm going to take the first number, 1, and I'm going to add 2, n minus 1 times. Should have drawn that 2, and let's go ahead and trace over it in blue. It's not really going to make too much of a difference, but for future reference. So whatever position line, I'm going to take the first number and add 2. 1 less that many times. So if I want to predict the 10th and the 100th terms, that means I want to find the, in this case, let's write this subscript in, let's do it in purple. So in the 10th spot in line, I'm going to take my first number, 1, and I'm adding 2, 10 minus 1 times. So I'm adding 2 9 additional times. That'll get me to the 10th spot. So ace of 10 is 1 plus 2 times 9. Ace of 10 is 1 plus 18. And ace of 10 is number 19. And this would prevent me from having to stop 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. So I know that if I count by 2s, I'll get there. But this helps me skip forward a little bit. And likewise, if I wanted to find the 100th, I would simply just say, okay, I need to take that first term, and I'm going to add 2 100 minus 1 times, or I'm going to add 2 99 additional times to get to position number 100. So 1 plus 2 times 99 is 1 plus, let's see, 100 times 2 is 200. 1 less twice is going to be less 2. So that's going to be 198. So my 100th number in the sequence is number 199. Perfect. And so now the pattern going up does the same thing going down. So if I went up, this is something that is going down. So I'm going to take, again, I'm going to first check for an arithmetic series. So I'm going to take the second number and subtract the first, so negative 321 minus negative 302. And I'm going to take negative 340 minus negative 321. Take the second minus the first, third minus the second. If there was more, I would keep checking each one because it needs to be constant. I know that's going to end up being plus a positive. And let's see, 302 minus 321, well, the difference is, looks like 19, so negative 19, plus plus. So now the difference here is going to be, again, negative 19. I have a common difference because it's the same number both times, so I know my difference is negative 19. It's going to help me write my formula. A sub n equals my first number, negative 302, and I'm adding my difference, so adding a negative 19, or I could just say minus 19, n minus 1 times. Boom. So we use this formula to predict the 10th and the 100th, which means my 10th position is going to be equal to negative 302, and I'm taking away 19, 10 minus 1 times, or I'm taking away 19 9 additional times. It's going to be negative 302 minus 19 times 9. Let's see, 19 times 10 would be 190. Take away that last 19, so 190, that'd be 180, 171. Perfect. So ace of 10, 2 negatives is going to make a bigger negative. That's 2 and 1 is going to make 3, 7 and 0, 1 and 3. So negative 473. And that's the 10th number in the sequence. If I subtracted 19, 9 additional times from that spot. And likewise, to find the 100th spot, I would simply take my starting term, I'd say negative 302, and instead of subtracting 19 9 times, I'm going to subtract it 99 times. Okay, so 19 times 100 would be 1,900 minus 19, that's going to be 1,881, if I did my math correctly. Yeah. So my ace of 100 Oh yeah. Kind of skip that middle step. But so negative 302 minus 1881. 2 negatives is going to make a bigger negative. So 2 and 1 make 3. 0 and 8. 3 and 18 is 21. Boom. There we go. And so I have two series right here. One going up where I'm adding a difference, one going down where I subtract a difference. They work exactly the same way. You might ask yourself, what happens if I don't have a consistent value here? Like if I take 2 minus 1, I get a positive 1. But if I take 5 minus 2, I get a positive 3. Well, what this means is there is no difference. There is no difference, so therefore, none of this applies. So we can't actually go further. We're going to have to check to see, is this something else? And we're going to see the something else is in the form of a geometric series. Now, all a geometric series is the same thing, but I know that if I tried to add and subtract, so 2 minus 1 is 1. 4 minus 2 is 2. I don't have a difference, so I can't find a difference, but I'm going to try the other method. I'm going to see, does it have a ratio? So I'm going to take 2 and divide it by 1, and I get a 2. I'm going to take a 4 divided by 2, and I get a 2. And if I divide the two numbers and I get the same thing, I know that my rate is going to be times 2, which allows me to set up this general formula that we had on the other page, a sub 1 times r to the n minus 1. Okay. So I'm going to take my desired term. I'm going to plug in the starting number in the sequence, which is a 1. And I'm going to multiply it times the rate, which in this case is 2. So I'm multiplying that 1 times 2 each time, n minus 1 times. So there's my formula. I'm going to predict the 5th and the 15th. Now these numbers are a little smaller because when we're multiplying, these get really big really fast. Or likewise, if we're dividing, they're going to get really small really fast. So we're not going to go too far with these. Let's go ahead and let's predict the 5th. So a sub 5 is equal to 1 times, nope, not times 5, times 2. 1 times 2. I'm going to do that 5 minus 1, or 4 additional times. So 1 times 2, 4 additional times. Okay, and if I know my two tables, that's going to be 2, 4, 8, 16. A sub 5 is 1 times 16, or just 16. And we can actually predict that by saying, okay, if I were to count out to the 5th, that'd be 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16. Yep, we're good. And the same thing is going to happen if we try and predict the 15th term. So that's going to give me 1 times 2, 15 minus 1, so 14 additional times. Okay? And so what you may want to do is you may want to bust out a calculator on this one. So 1, let's see. Let's see, we have 2 to the power of 14, which is going to give us 16,384. Let's move this over. Actually, I'm going to slide this over here. 16,384. Which means my 15th term is actually 16,384. And now again, we could verify that if we wanted to actually sit there and count out times 2 15 times. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Hold up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Not do the 15th because we started out with the 1. 16,384. So you already saw the error with doing it via the brute force method, is if you don't count right, you're going to get the wrong answer. So typically we want to rely on shortcuts like this because these are more reliable as opposed to did I count the right number of multiplication steps. I didn't plan on showing you that kind of mistake, but it worked out well to kind of prove our point. So let's go ahead and let's work on the next one. Instead of going up where we're multiplying, let's take a look and let's assume, well, I know that it's not going to be a difference because 100 minus 1,000 is negative 900, but 10 minus 100 is negative 90. I notice that my difference is not constant, so there is no difference. However, if I take 100 divided by 1,000, I get 1/10. If I take 10 divided by 100, I get 1/10. So my difference in this case is I'm dividing by 10. Nope, not difference, my rate. My rate is I'm dividing by 10. And this is how we show divide by 10. Multiply by 1, divide by 10. So I'm going to take my formula, a sub n, my first number, which is 1,000, and I'm going to multiply that, or actually in this case, divide by 10, n minus 1 times. Perfect. Let's see if we can't flesh this out. So my fifth term in this series is going to be 1,000, and I'm actually dividing by 10. Let's see, 5 minus 1, so 4 additional times. 1,000. So 1/10, 4 additional times is 1,000 times, well, that's easy because I can just make it 4 zeros. So 1, 2, 3, and 4. Okay, so I know my fifth term is 1,000 divided by 10,000. So I know the fact that I'm going to have some zeros, let me cancel these out in blue, are going to cancel themselves out. So lo and behold, my fifth term is 1/10, conveniently speaking. We can verify that by saying first term, divide by 10, divide by 10. If I divided by 10 for the fourth term, I would have 1. If I divided by 10 again for my fifth term, I'd have 1 divided by 10. So it works out. Likewise, if I take my 15th term, I'm going to take my first term and divide it by 10 14 additional times. So 15 minus 1. Okay, so that means my a sub 15 is 1,000 divided by 1 over, I have 14 zeros. So let's count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Awesome. Which means that 1,000, I have 100, 1,000, million, billion, trillion. And we know that some of these, those 3 and those 3, are going to cancel out. So my 15th term is actually 1 over 100, 1,000, million, billion. It's 1/1,000,000,000th. Don't actually need to put parentheses around that, but it works out. Yep. And so the last question that you might ask is, what happens if, let's say, I'm oscillating? I have a negative, a positive, a negative. What does that mean? Well, all that means is the fact that our ratio here is found the same way. If I can't find a difference, we can already see that this isn't going to be a difference. If I take my ratio and I take 15 divided by -5, I get -3. If I take -45 divided by a positive 15, I get a -3. So my rate is a negative number. which means sometimes it's a positive, sometimes it's a negative, depending on how many times I've multiplied by that negative value. And I just work through it. So I get my a sub n is, in this case, my first number, so -5. And I'm multiplying times a -3. And so you see why we put parentheses on this thing, n minus 1 times. And so if you want to find your fifth number, you can ask yourself, okay, well, before I even begin this, I'm multiplying a negative number 4 additional times. So a negative times a negative times a negative times a negative. How many are 5 negatives total? Well, you're going to end up with a negative value. Because many people often get confused with, well, what is the sign of my final answer? Well, I know negative an even number of times means they all pair up, so that's going to be a positive times a negative. Let's see, 3 squared is going to be 9. 9 squared is going to make me 81. Positive 81, which means my fifth term is, let's see, negative 405. Perfect. And if we get 15, take -5 and I'm multiplying it times -3. Instead of 4 additional times, it's 15 minus 1, so 14 additional times. Okay. I can't quite do this one in my head, so I'm going to take -5. I know it's an even number, which means my 3 to the power of 14 is going to be even. But let's take -3 to the power of 14. We get a really big number like this. So let's see, that's 4, 7, 8, 2, 9, 6, 9. I'm multiplying that times a -5. Let's see, and so I get 845, 914, -23. So -23,914,845. There you go. Okay, so today what we're doing is we're doing the second part of our series introduction. And this is saying that we're going to take an arithmetic series and we're going to sum up all possible values over a certain span. Now, that being said, we can't sum it over an infinite span because as a series is continually going up, if I continually add larger and larger values, I'm going to approach infinity. So again, an infinite span doesn't work with an arithmetic series. But I can do it over the course of several numbers, like from 3 to 6 or from 1 to 5. I can do it over a small span. And this is going to be shown in what we call sigma notation. Now, sigma is just a letter in the Greek alphabet shown as what looks like a giant, slightly awkward E. Again, sigma notation just says, hey, it's in this letter format. And now the way that we read this is here is the formula, here's the pattern that's going on. I'm going to start with the term right here. So I'm going to start on the third value, and I'm going to go all the way to the sixth value. So in essence, let's go ahead and let's label these. So I have my starting value, or my starting term, and I have my ending term. And so now the long way to do these is to add up each individual value as we go on. So if I were to take the 2x and I were to fill it in one at a time, one at a time, one at a time, it would look something like this. And it would be the sum of 2 times x, so 3, 4, 5, and 6. And I would take this value for x and say 3, and then I would increase it by 1 until I hit this. So 3, increase it by 1, 4, increase it by 1, 5, increase it by 1, 6, and I stop. And I evaluate out each one of these and say 2 by 3 is 6, 2 by 4 is 8, 2 by 5 is 10, 2 by 6 is 12. Add all of these up, and I get, let's see, 8 and 12 make 20, 36. And so that is all sigma notation is doing. When we sum a series, given this format, we're saying, hey, plug in each one of these values into the equation until you hit that number, and then add up all of your answers. Now, that being said, when you have larger and larger values, we're going to start out with some smaller values like 1 to 5, something that we could easily do by hand. But if we start going off like, let's say, the first 50 or the first 100 or the first 1,000, we want to be able to do it in a faster method. So what we're going to do is we have a shorthand formula right here that allows us to sum the series without having to calculate this out 100 times for, let's say, the first 100 series. So we're going to start out with, we're basically taking the number of terms we have. So top number minus the bottom number. So in this case, it would be 6 minus 3, which would be 3. But I know I'm doing it 4 times. So 3 plus 1 gives me 4. I cut that in half, and I multiply it by the sum of both my first and my last term. So when I plugged in my first number, when I plugged in my 3, and when I plugged in my last number, 12. And just to kind of show this by hand, if we were to do that, that means I would take 6 minus 3 plus 1 all over 2, my first term, 6, plus my last term, 12. So that would mean that I would have 6 minus 3 is 3, plus 1 is 4, divided by 2 is 2, times, let's see, 6 plus 12 is 18, 2 times 18 is 36. So again, it's a formula that allows us to save time. Now, we know the fact that this is not a complex process. We can do it by hand. And in fact, most standardized tests, you'll see questions like this, and they know that you're going to get it right if you know how to read it. The idea is that most standardized tests are timed, so they want to see, do you know how to expedite the process? And for an arithmetic series, that's what we're doing right here. So now that we've kind of gone over what we're doing, let's go ahead and let's try out a few. So what we want to do is we want to write this in sigma notation and then sum. So that tells me I need to figure out the pattern here. And I know that my pattern, as we've discussed prior, is going to be, I'm going to take the first term and I'm going to add the difference times n minus 1. So in this case, my first term is going to be a 1. And my difference is I'm adding 2 each time. 1 plus 2 is 3, 3 plus 2 is 5. So plus 2 times n minus 1. Perfect. So I have my pattern. So I'm going to set it up and say, I'm going to sum the series from the first term, my variable being n, so from n equals 1 all the way up until n equals 5. And notice I don't write n equals 5 on top because I've already denotated which variable I'm changing. What's the formula? Well, it's this one right here. 1 plus 2 times n minus 1. So what I could do is, like I said, I could do it via the brute force method. I could say, okay, 1 plus 2 minus 1, 1 plus 2 minus 1. Actually, let me see how many times I'm going to have to write this. 1, 2, 3, 4, 5. And I know I could get it done this way. And in essence, this would make it, so what, 0 times 2, that's 1 plus 0, that's 2, or 1 times 2 is 2, so 1 plus 2, 1 plus 2 times 2 is 4, 1 plus 6, 1 plus, that's 4 times 2 is 8, so 1, 3, 5, 7, 9. You notice how we're getting our pattern as we're going through it? And if I sum all those up, I get, so that's 4 plus 5 is 9, plus 7 is 16, is 25. So I know I can do it via brute force, but again, we're not after the brute force method. What we want to do is we want to figure out, can I speed this up? So what we're going to do is we're going to say, hey, if I'm finding the sum from n equals 1 to 5, I'm going to use this, and I'm going to say it is equivalent to my top number, which is going to be 5, minus my bottom number, which is going to be 1, plus 1 divided by 2 times my first term, which in this case for n equals 1 is going to be 1, plus, let's see, my last term. My last term, as I evaluated out the formula, is going to be 9. And that is actually what I'm going to do. The sum of my ace of n series is going to be equivalent to this. So let's see, 5 minus 1 is 4, plus 1 is 5, divided by 2, so 5 halves times 10. So 10 divided by 2 is 5, times 5 is 25. And we can already see that that takes a lot less writing. It's a lot faster. And that was only for 5 terms. Now, if we did that for, let's say, first 50th, this would be much faster. So let's do one more. So the second one, this is still an increasing formula. And first and foremost, I know I need to figure out what the pattern is. So what I'm going to do is I'm going to plug in my first number, so negative 300, and I'm going to figure out what the difference is. Let's see. I go from negative 300 to negative 270, so I'm going up because my negative is getting smaller. I'm going up by 30. If I add 30 to negative 270, I get negative 240. So I know for sure I'm adding 30 each time. And so that is what I'm going to use in my sigma notation. So I'm going to say, hey, I have a process from, in this case, the second term to the sixth term. And I'm going to use this formula, negative 300 plus 30 times n minus 1. And now I'm going to expand this into only 2 terms, into my starting and my last term. Because remember, I only need to figure out what ace of n is and ace of m when I plug in the first and when I plug in the last. I don't actually need to find out all of these terms in the middle. So I'm going to say negative 300 plus 30 and I'm going to plug in my first term, 2, and my last term, 6. So 2 minus 1 is 1, times 30 is 30, negative 300 plus 30 is negative 270. And yes, we can verify that that is a correct formula for our pattern because we got 270. Unfortunately, we don't have the 6th number in the sequence, so we're going to have to figure that one out. So 6 minus 1 is 5. 5 times 30 is 150, which is half of 300, so I'm going to have negative 150. And I'm going to use these 2 values in my formula. So I'm going to say the sum of my ace of n series from 2 to 6 is equal to, I'm going to say my top number, which is 6, minus my bottom number, which is 2, plus 1, all divided by 2. And I'm going to take my first term, which in this case is negative 270, and I'm going to add it to my last term, which in this case is negative 150. Perfect. So what I get is I get 6 minus 2 is 4, plus 1 is 5, so 5 halves, negative 270, negative 150. Let's see, that's going to be negative 370 plus 50, that's going to be negative 420. Let's see, half of 420 is going to be 210, so that's 5 times negative 210. So 5 times 200 is going to be negative 1,000. 5 times 10 is going to be 50, so 1,050. Perfect. And that saves us from having to work every single one of these and adding them all up. We got it done right there. So let's go ahead and let's try one. Instead of going up, is going down. So in this case, I'm going from 100 to 85 to 70, and as I keep going on, I'm going to keep going down, and something fun's going to happen at one of these terms out here. I'm going to go from a positive number to a negative number. So we're also going a little farther out. So our brute force method is not going to work nearly as fast. So first and foremost, let's figure out what our pattern is. What is the formula for what's going on? Start out, I know my first term is 100. In this case, I know I'm going down, so my d is going to be subtracted. I'm not going to be adding something each time, I'm going to be subtracting it. Looks like I went down by 15. If I subtract 15 again, I'll get to 70. So minus 15 times n minus 1. And I'm going to use that. So I'm going to write sigma notation from n equals, in this case, 3. So I hopefully, when I plug it in, I'll get 70 as my first one, to 13 of 100 minus 15 n minus 1. So I'm going to expand this. And just to double check to make sure I did this correctly, I'm actually going to plug in the 3, but I know for my first term, I should get something is equal to 70. I don't know what the bottom one is going to be unless I count by 15s, which again, I could via brute force, but we're going to use our formula and see if we can get it to work out. So 100 minus 15, 100 minus 15, for my first term 3, and for my last term 13. Okay. So 3 minus 1 is going to be 2 times 15, that is 100 minus 30, which is in fact 70. And for my next one, 13 minus 1 is 12. 12 times 15, let's see, 10 times 15 is 150. 2 times 15 is 30, 150 and 30 make 180. So 100 minus 180 is going to be negative 80. So notice that these are almost the exact opposites of each other. So I've crossed 0 and pretty much firmly gone directly on the other side. So let's go ahead and let's figure out. So my series from the 3rd term to the 13th term of my a sub n series. And now one of the things you might be asking is, why do I write it like this? Because before I actually evaluate out what the series equals, I have to continue to write, this is the sum of the series. I haven't actually added it up yet. I'm still saying, hey, I got to do something. So I'm going to, see, I'm dividing something by 2. I'm going to take my 13, and I'm going to subtract my 3. So 13 minus 3 plus 1. Plug in my 70 and my negative 80. And I'm going to add these two numbers together. So I write equals this, because this, whatever this equals, is the sum of the series. If I write the summation and I start to write this, I'm saying I'm summing this series with no n. It doesn't mean anything. I have to actually write the sum in sigma notation is equal to this. So 13 minus 3 is 10, plus 1 is 11, so 11 halves times negative 10. So half of 10 is 5, so 11 times negative 5 is negative 55. Perfect, and there we go. So having seen that, what I want you to try is I want you to try the next set. So go ahead and pause the video and give it a shot, and I'll put the work here in a second. Make sure to see how you did. Okay, so let's double check. My formula is going to be first plus the difference n minus 1. I know in this case my first term is 2, and I'm going up by 8. Actually, not up by 8. I'm going down by 8, so minus 8 each time. And there's my pattern. I'm going to sum my series from the 5th to the 15th of negative 2 minus 8 and minus 1. Some of you might also be saying, can't you simplify that? And yes, you can. Again, I just went ahead and I plugged it in. It's going to save us a few steps in the beginning. It's going to cost us a few steps later on. Doesn't really matter. That's up to you. So now my 5th term and my 15th term. I bet you if I keep counting by 8, I could figure out my 5th term. So 10, 8 minus 8 is going to be negative 26, minus 8 is negative 34. So I bet you that's going to be a negative 34. So 5 minus 1 is 4, times 8 is
32, so negative 2 minus 32 is negative 34, correct. But again, if I count out to the 15, I might make a small error, so I'm just going to go ahead and use the formula. So that's a negative 2 minus 15 minus 1 is 14 times 8. Let's see, that'd be 10 times 8 is 80. 4 times 8 is 32. 80 and 32 make 112. So negative 2 minus 112 is going to be negative 114. Perfect. And those two values allow me to go ahead and work on the rest of this. So from the 5th to the 15th of my series is going to be, I'm going to take my 15, subtract the 5, add 1, divide by 2. And I'm going to add my two values together. So my negative 34 and my negative 114. That's going to give me 10 plus 1 is 11 halves. Let's see, negative 34 plus or minus 114, they're going to be combined together, make a bigger negative. So that's negative 118, negative 148. Half of 148 is going to be 11 times negative 74. So let's see, that'd be 10 times 74 is going to be 740. With another 74, that's going to be, let's see, 740 plus 70 is going to be 810, negative 814. There we go. So how'd you do? And then the last question is really what you're going to be seeing on if you take this as a standardized test. So as a challenge, we know we can do this via brute force, is we can count all the way to 100 and add all those numbers up, but the bet is you're going to make some sort of arithmetic mistake at some point. So go ahead, try this one as a challenge. Pause the video, resume it when you're done, and let's see how well you did. Okay. So a sub n equals a sub 1 plus the difference times n minus 1. Negative 24, and I'm adding 24. Times n minus 1. Perfect. So from 1 to 100 is equal to negative 24 plus 24 times n minus 1. So from 1 to 100. So that's 0. That cancels out. That's negative 24. Good. We found the correct formula. Let's see. If that was 100 times 24, that'd be 240. One less than that is going to be, let's see, 220, 216. So it's going to be negative 24 plus 216. And 216 minus 24, that'd be 212. So that'd be 202, 192. Perfect. So the sum from the 1st to the 100th of my series is going to be I'm going to take 100 minus 1 plus 1 divided by 2 of my first number, negative 24, my last number, 192. Scratch that. I think I multiplied by 10 here. It's a lot bigger of a number than that. So scratch that. That is negative 24 plus, let's see, that is actually going to be 2400 minus 24. That's going to be negative 2376. So 2376 minus another 24 is going to be negative, or positive 2352. So I got that. So plus 2352. I was like, hold on, the 100th term of the sequence is not 192. We're a little low there. So 2352 minus 24. Let's do this again. So that's going to be 12, make that a 4. It's going to be 8 to 23, 28. These are going to cancel out, so 100 divided by 2 is going to be 50 times 23, 28. So 23, 28 times 50, that's all going to be 0, so just hold my 0. 40, 10, 14, 15, carry my 1. So that's, hold on. Hold my 0. That's going to be 40, carry my 4. 10 plus 4 is 14, carry my 1. 15, carry my 1 is going to be 16 plus that. It's going to be 10 plus 1 is 11. So it's going to be 116,400. There we go. How'd you do?